My name is Alistair Plotnick, and today I will be presenting the black hole app. So first we have the introduction with the purpose, and the purpose was to determine the net force acting on a star due to a black hole, calculate the mass of a black hole using the net force, and to determine the initial velocity of a ship that can leave a planet and escape the grasp of a black hole without crashing. So the basic models used were Newton's second law of momentum principle shown to the right, the breakdown of a net force into parallel and perpendicular forces, which allows us to consider the different directions in which the force of the black hole acts on the objects, and the law of universal gravitation, which is used to calculate the mass of the black hole most directly, and we rearrange this formula to isolate the mass of the black hole, and those are also shown to the right. So for part one, the system versus the surroundings, the system is just the star and the surroundings are the black hole. So our initial conditions and assumptions in part one, the time between the data points in our trajectory is 1 day or 86400 seconds. The mass of the star is 2.08 times 10 to the 30 kilograms, and the net force on the star is solely caused by the black hole located at the origin. In part two, the net force on the spaceship is caused by the planet/black hole. The mass of the planet is 9 times 10 to the 28 kilograms, and the mass of the black hole is retained from part one, and the mass of the spaceship is 7 times 10 to the 10th kilograms. So here are the details of the part 1 code. It can be found in the description, and here it is right here. Results from part 1. So the mass from the computational model was 1.09629 times 10 to the 34 kilograms. The net force was 8.44055 10 to the 28 newtons. The net force in the parallel direction was 3.35784 10 to the 27 newtons, and the net force in the perpendicular direction was 8.43569 times 10 to the 28 newtons. And you can see on the right what the model looks like. So what does it mean? Net force versus momentum. The net force in the parallel direction changes the magnitude of the momentum. The net force in the perpendicular direction changes the direction of momentum. The components of the net force, in this case just gravity, change the rate of momentum, and changes the net force changes the rate of momentum due to the equation of F net equals change in momentum over change in time. So systems and surroundings for part 2. For the planet as a system, the surroundings is the spaceship and the black hole, and the forces are just the force of gravity due to the black hole and the force of gravity due to the spaceship. And then for the spaceship as a system, the surroundings are the planet and the black hole. The forces are the force of gravity due to the black hole and the force of gravity due to the planet. So here are the details of code. Part 2 of the code. Again, it will be in the description, and here is a screenshot of it. And then here are the results of part 2. The set of values that I used in this example were that the ship speed in the x direction was negative 3.8 times 10 to the 7th meters per second, and the ship speed in the y direction was 3.9 10 to the 6th meters per second. And the blue line is the planet, and the pink line is the ship. And then, yep, the ship is now, in this screenshot, 1.23688 times 10 to the 11th meters away from the event of the horizon of the black hole. So what if entering into orbit? The closest I found for an orbit of the spaceship was that the ship speed was in the x direction of 1.856 times 10 to the 6th meters per second, and the ship speed in the y direction was 1 times 10 to the 7th meters per second. So possible sources of error, a computational model will not perfectly predict the real motion, which does not enact an ideal manner of motion because motion is not perfect. So the conclusions, the components of the net force change the rate of change of momentum and the direction of the momentum, and we can use the universal law of gravitation, Newton's second law, and the principles of curving motion to both escape a black hole or escape its orbit.